So let's talk about relativity, which is basically a bit simple in concept. It's just how different observers see the same event. And we're going to talk about two different kinds of relativity that are out there. First kind is easiest, something we call special relativity. And this is both these kinds of relativity we're going to talk about. They were both theorized by Einstein. And every experiment we've done since Einstein theorized that they existed, these concepts of relativity, have proven that Einstein was right and relativity exists. So special relativity is actually pretty easy. It only says two things. It says that the laws of physics are the same in inertial reference frames. And that word inertial just means that you're not accelerating. So you're going at a constant velocity. So as long as you're not accelerating, all the laws of physics will be the same between your different reference frames. Second thing special relativity says, speed of light in the vacuum is always c. It's a constant that we usually round up to 3 times 10 to the 8th meters per second. This is all special relativity says. These are the two definitions of special relativity. So if someone were to ask you, you'd just put these two items as being the definitions. Now there's some side effects of this. Okay. Some side effects and some terminology to know related to special relativity. First, there's this concept of something called simultaneity. And this tells us that two events that happen are simultaneous if an observer measures them occurring at the same time. This is a little bit weird, and the implications of this aren't absolutely clear. So what I'm going to do, I'm going to put a link in the description of a video, another YouTube video about simultaneity that kind of makes it a little bit more clear. Now, some other side effects that we have of relativity, and in particular special relativity. So we know that there's this concept of something called time dilation. Time dilation is basically a result of the above two assumptions for the special theory of relativity. Now, what this tells us is that observers that are moving so they have some speed v. They have to be moving at a constant speed v. They can't be accelerating because then our special theory doesn't apply. But these observers that are moving, they don't measure the same elapsed time for an event. That's kind of the official definition of time dilation. Some slightly maybe simpler ways to think of it. Time is relative. Time changes based on where you're observing it from, where your reference frame is. Everything is relative. That's why we call it relativity. Time is relative, and basically this results in moving clocks running slow. And we can quantify this. So we can quantify this with an equation. The equation for time dilation tells us change in t is equal to change in t naught divided by the square root of 1 minus v squared over c squared. And we can do some simplifications of this, and we can define what all these variables actually mean. So all of these variables, change in t naught, that's going to be something called the proper time. This is an observer that's at rest relative to an event being observed. The other variables we have in here, delta t is the time that's measured by, let's say, an earthbound observer. And then v is the speed that your proper time observer is actually traveling with. So what does that actually mean? What does all this mean? Well, let's do a simple little example. Let's do Earth sitting here, and we'll put a person standing on Earth. Okay, so delta t is going to be the time that this guy on Earth measures. And let's say that somebody else has left Earth and blasted off in a rocket ship. It's pretty clear that this rocket ship is moving away from Earth with a velocity v. So this person is traveling. If they look at their clock, they're going to measure a different time on their clock as a result of them moving. Remember, moving clocks run slow. So the proper time is the observer that's at rest relative to the event being observed. So the clock on the ship is the event that we're observing, and this person on the ship is going to measure the proper time, the time relative to the reference frame that's actually moving. Okay? This seems a little bit weird. This is a strange concept that a moving clock runs slow, but we have this equation we can use, and this equation right here, every time we've actually measured time dilation, this fact that moving clocks run slow, we found that this equation is valid. And to make it a little easier, we've actually simplified it a little bit by introducing a variable called gamma. This gamma, Greek letter gamma, has a different name, couple different names. We'll stick with gamma for now. And it's equal to 1 divided by 1 minus the square root of v squared, 1 divided by the square root of 1 minus v squared over c squared. So we can use this gamma and plug it in for our proper time equation. So we can simplify this a little bit to delta t is equal to gamma times t naught. For those that are interested, this gamma, one of the more popular names, if you do some Googling, you'll find that this is something called a Lorentz factor, which we use to convert between different kind of frames of reference, which is all we're doing here. So we know that a moving clock runs slow due to time dilation, and this is a side effect of special relativity. There's other side effects of special relativity too. Another side effect we have is something called length contraction. Now in length contraction, we have a similar effect happening where we have some length is equal to L naught times the square root of 1 minus v squared over c squared. And this equation again, L naught is the proper length. And this is length measured between 2 points by an observer that's at rest relative to both points. And L is the length measured by an observer on Earth. So let's see that example again, in particular with our rocket ship. So let's draw our Earth. We have our person standing on Earth. They're going to measure the length of this rocket ship that's flying away. And we have our person standing on our rocket ship. So our person standing on our rocket ship is at rest relative to this rocket ship. They're going to measure the length of this rocket ship. Their length that they measure is going to be L naught. And that's the proper length because I'm at rest relative to both points of the rocket. But the person on Earth, when they look at this rocket ship, the person on Earth is going to measure a different length. They're going to measure the length from their perspective. So we have person on Earth measuring a length, and we have the person on the rocket ship measuring a length. And those lengths are going to differ. They're going to differ according to the Lorentz factor again, or 1 over the Lorentz factor. So that's our equation for length contraction. And this happens as well due to special relativity. We have other equations, other side effects of special relativity. We have something called relativistic momentum. So this is going back to physics 1, where you study momentum. And what we usually don't realize in that first initial study of physics is that your momentum equation isn't actually right. Momentum is actually equal to this Lorentz factor times mass times your velocity, where m has to be your rest mass, so how much mass you have when you're not moving. Turns out mass changes when you move, and u is your velocity relative to your observer. So this is how fast you're going. So your momentum is actually slightly different than just mass times velocity, because you have this gamma factor in here, this Lorentz factor. Remember, gamma, again, is 1 divided by the square root of 1 minus u squared over c squared. So the reason we don't usually use this gamma is because this is typically a very small effect. Typical velocities, u, however fast you're traveling, is usually much, much less than c, so there's no reason to use this Lorentz factor. But there are some side effects that we can see here. This relativistic momentum equation. If u gets really, really close to c, as this approaches the speed of light, we end up with 1 over the square root of 0 for our gamma. If this is the case, we have 1 divided by 0, which is a super small number, which approaches infinity. So what this tells us is that as your velocity gets up to being close to the speed of light, your momentum relativistically becomes infinity. What that means, what that tells us, is we can't get a momentum up to infinity, that we just can't do that. So any object with mass according to this relativistic momentum equation, cannot reach the speed of light. Because if they could, then their momentum would become infinite. Cannot reach the speed of light. So this is a crazy result. Means we'll never be able to travel at light speed. And then finally, we have one last equation to involve in relativity. We have relativistic energy. So all of our energy equations from last semester, we need to add on this relativistic effect. And again, we don't usually do this because usually we're not working at speeds where this relativistic Lorentz factor becomes important. Energy is now equal to gamma times mc squared. So this is the full-on correct version of Einstein's equation for energy. The more typical one that we see, probably Einstein's most famous equation, E equals mc squared, still is a relevant equation. It's just telling you rest energy. It tells us energy of a non-moving object. As soon as you start moving, technically, you need to plug in this gamma Lorentz factor. The other useful aspect of this E equals mc squared equation we use in nuclear power, actually. Because what this tells us is that energy and mass are the same thing. We can convert between the two by breaking up mass into energy. And even a small amount of energy, a small amount of mass becomes a huge amount of energy because of this c squared. Speed of light is a very big number, so when we multiply a small mass times the speed of light, we can get out a really, really big energy. And this is what we do in nuclear power plants. And finally, last but not least, let's look at the work energy theorem and how it works in relativity. So hopefully we remember what the work energy theorem is, what we probably don't. So this tells us that the net work you do on an object is equal to that object's change in kinetic energy. And relativistically, an object's change in kinetic energy is the energy minus the rest energy. So, according to relativistic energy theory, W net is equal to change in KE is equal to gamma times mc squared, this Lorentz factor times mc squared, minus mc squared. So this will allow us to calculate energy relativistically of something like light. It can get a bit more complicated than this, but we're just interested in the basics for the purposes of this one.